Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll. Today we're doing the Q&A video associated with, I think it was the 8th idea of entanglement, quantum entanglement. The 7th idea we did was quantum mechanics, and we gave you basically some of the textbook stuff about wave functions and how they collapse when you measure them. In video number 8, we went a little bit deeper into the idea of entanglement, which is something that truly separates quantum mechanics from classical mechanics, and it let us talk about some of the more modern formulations of quantum mechanics, formulations that are purportedly a little bit more rigorous and well-defined than the Copenhagen interpretation that you read about in textbooks. Opinions differ about whether or not that is true, but I'll, in this video, answer a couple questions about entanglement generally, and then go in a little bit to more detail about how things work in the Manyworlds interpretation, which is my favorite one. I didn't do this in the original video because I've done things like this on videos online elsewhere, but there's a completist aspect that indicates that we should probably do it here. So I thought about the different questions that were asked, and I think that it would be useful before diving into the answers to talk a little bit more about this example of quantum mechanical spins, because spins really, when you talk about entanglement and the wave function of different parts of the system interacting with each other in different ways, spins provide a very, very nice explicit example that you can control much better, that you sort of know what all the different options are in a way that we talk about the position of something or the momentum of something. That's harder to do, for the basic reason that there are an infinite number of possible positions you could measure, but there are only two outcomes you can get when you measure the spin of, let's say, an electron. There are higher spin particles, but for an electron, there are only two possible outcomes you could get, which is why spins are characterized by qubits, quantum mechanical versions of bits. A bit is either 0 or 1, classically. Quantum mechanically, it's some superposition of 0 or 1. And spins are represented quantum mechanically by qubits. A spin is a physical thing, a qubit is an abstract notion, but they line up in this particular way of thinking about things. So let's talk a little bit about how you find out about spins in the first place and what this teaches us about spins, because again, I don't like to keep anything in suspense. We're going to use spins to think about the uncertainty principle in quantum mechanics in a slightly different way, what superpositions mean, what basis states are, which I mentioned in the previous Q&A video, and then we can use that technology to talk about entanglement in a more detailed way. So we measure the spin of a particle by something called, well, one way to do it is something called the Stern-Gerlach experiment. And I'm not going to go into great detail about this. I'm going to give sort of a theorist's version of the Stern-Gerlach experiment. This is an experiment that was actually done by Messrs. Stern and Gerlach, but we're not going to go into the experimental details. The basic idea is that if you have a magnetic field, and it is an inhomogeneous magnetic field, so it's sort of more pointy at one end than the other. So it's like a set of lines of magnetic field that sort of are originally spaced out and then they come together, okay? And you pass an electron through it. The spin of the electron is a little spinning particle that has an electric charge, so it's a little magnet. And it will be deflected either in the direction of the magnetic field or opposite to the direction of the magnetic field if it were spinning such that its axis were pointing along or against the magnetic field. So I'm not going to try to draw an accurate depiction of the magnetic field because that's hard. So here's my magnetic field, BZ. So we're thinking that we're in a little coordinate system here. You'll see Y, X, Y, Z. Our electron, our spin, how should I draw the electron? I'll just say E minus. The electron is moving along the y-axis, and it encounters this magnetic field. And the point is that you might think, I'm not sure if you should think this or not, but you might think that if the electron is a little spinning magnet, it has a magnetic pole and it could be pointed anywhere, right? The pole is aligned in some direction. And therefore, when it goes through, it could be deflected up or down or any intermediate value, right? But quantum mechanics comes along and says, in fact, the electron only ever goes slightly up or slightly down. And this is what we would call spin up or spin down, okay? There are two possibilities. That's why it's a qubit. That's why it's a quantum mechanical version of 0 or 1. 0 is spin up, 1 is spin down. Now, there's actually subtleties here, whether or not you need quantum mechanics to explain this two-valuedness rather than infinite number of continuum of values, but we're just going to take it as a fact that we're not comparing classical mechanics to quantum mechanics. We're just saying this is the quantum mechanical answer. So you represent then the state of the particle, psi, by some combination, alpha times spin up plus beta times spin down. This is the wave function of the spin. This is a slight modification to look less scary of the Dirac notation that Paul Dirac invented. He would have written alpha up, and then so there's a line and a right angle bracket plus beta down angle bracket. And this is called a ket, this particular notation, because this is half of a bracket. So there are both bras and kets. A bra looks like this. Oops. That's a bra for physicists. This is a ket. We're not going to use any of that notation, okay? But I'm just going to use this simplified parentheses notation. It's more than good enough for what we want to do. Okay. And you know that these numbers, alpha and beta, these are two complex numbers. These are the amplitudes for observing the particle to be spin up or spin down. So the probability of, in this experiment, measuring spin up is magnitude of alpha squared. Probability of measuring spin down in this experiment is the magnitude of beta squared. And therefore you know that alpha squared plus beta squared equals 1 because the sum of the probabilities has to be equal 1 and you only have two choices. Good. So I think that all that, I sort of glossed over that, but I mentioned things like this before. But now let's do something a little bit more complicated. We measured there the spin in the z direction. So we talk about spin up. We always imagine the z direction is pointing towards the sky. So we talk about spin up versus spin down by measuring the spin in the z direction. But we could also measure it in other directions. We could measure it in the x direction. It's hard to measure it in the y direction because the electron is moving in the y direction. But x is easy enough. So let's do the following experiment. Let's send the electron in. Okay. Let's measure it in the z direction, so let's do what we just did. And I'm gonna run out of room if I keep drawing all the different options here. So let's just imagine that what we got was spin up. Okay? I can do better than that. We got a spin up outcome. Good. But now, and again, remember x, y, z, now let's measure again the spin, but this time with respect to, I suppose I should draw it the other way around to be completely fair, the x magnetic field oriented in the x direction, okay? So then, again, it's going to split. And in fact, you could get, I'll just be consistent and draw it as a solid line. You could get either, spin right if you want, or spin left. So let's call this spin, let me see, right? All depends. It's not gonna, the notation is not going to look very good, but I'll call that spin right and spin left. Okay, you get the point. It turns out that if you do this, if you measure the spin in the z direction and you get spin up, then every time that you put it in the x direction spin measurement device, you will get either spin left or spin right. That's spin oriented along the x-axis, and you cannot predict which one you are going to get. Okay, just keep that fact in mind again. And then let's say that you measure spin left. Okay, let's say that's what you measure, and then you decide to do it again, the same electron, and measure it in the z direction. Okay, so we had the electron, we measured in the z direction, we found it was spin up. We measured it in the x direction, we found it was spin left. Now we're going to measure it in the z direction again. You could potentially think, I don't know if you would think this or not, I'm not trying to put ideas into your head, but you could potentially think that there were two separate things, one called the spin along the x direction and another called the spin along the z direction. In that case, you would think, okay, I've measured the spin along the z direction, it's up. I've measured the spin along the x direction, it's left. Therefore, if I measure the z spin again, it will be up again. Because if I didn't do this x direction thing, if I just did this, if I just had an electron come in, measure it along z, and I find that it is spin up, then if I measure it along z again, I will always get spin up again. This is a reflection of the fact that this measurement, in some sense, measures this going through, well, let's be super duper clear about this because we're trying to be accurate here. Going through the electric field, going through the magnetic field does not measure the spin of the electron. It evolves the wave function of the electron into two components that are separated in space. What we imagine is that we then measure it, okay? So it's not the splitting that measures it, because that does not entangle it with anything. But when we actually measure it, we need to entangle it with the environment. So we have some screen or some electric field monitor that has an arrow that says, oh, it went left, it went up, down, whatever it did, okay? So we're imagining that we both put it through the magnetic field and measured the spin of the electron. So just according to our old-fashioned Copenhagen way of thinking, when we measured it and we saw that it was spin up, the wave function collapsed, and it's now spin up. That's what it is. So when it goes through BZ again, it's always going to measure spin up. It's not going to be a superposition of both. Whereas what we find here, that might be what you think, that we measured spin up and that's done with it. What we actually find here, if we go through the Z magnetic field again, is an equal superposition of spin up and spin down. Okay, so putting the electron through the X direction magnetic field and measuring it to be one thing or the other thing turned it back into a superposition of spin up and spin down in the Z direction. So what that means is, and maybe this is not a surprise at all, again, I'm not telling you should be surprised, what it means is there are not two separate things, the spin along the X direction and the spin along the Z direction. There's only one thing, the spin of the particle, and when you measure it, you collapse it into some state that is either spin up or spin down with respect to the direction in which you're measuring it. And the way that we express that is the state that is spin up, that we've written like this, we can write as 1 over the square root of 2 spin right plus 1 over the square root of 2 spin down, spin left. So what this notation means is that this is a wave function. This is psi. You might want to call it psi for a spin up spin electron. And you can rewrite it as in terms of the left and right bases. And if you had gotten spin down, it would be 1 over square root of 2. These are conventions that we work out, and I'm skipping steps. Spin right minus 1 over square root of 2 spin left. So in either one of these two cases, if it was spin up or spin down, when we measure it along the X direction, there's a 50-50 chance that we're going to get spin left or spin right in the X direction, because these are the coefficients are 1 over square root of 2 with a plus or minus out front. Squared, in either case, you get a half. So there's half of a chance of getting it left or right. So there's yet another way of thinking about this. If you stare at these equations, remember Hilbert space, the space of all wave functions, is a vector space. Okay, you can add them, scale them by numbers, etc. So what this is telling us is we can write the vector space for Hilbert space of the qubit, of the single spin, in terms of basis directions spin up and spin down. And we can express any wave function psi, let me give it a color. Any wave function psi is just a vector in this vector space. So it has, if you did this, this would be, if you wrote psi as alpha spin up plus beta spin down, this component would be alpha, this component would be beta. Okay, there you go. And these equations telling you that spin up is a superposition, a combination, a sum of spin right and spin left, and likewise for spin down, can be thought of as saying, I hope I'm going to get the signs right here, I'm, again, making this up as I go along, but basically it's saying that spin left and spin right are two different axes in this same vector space. Two axes that are rotated with respect to what the old axes were. So the axis that we label spin right might be like that, and the axis we label spin left might be like that. You can actually work out what they are. There's a 50-50 chance that I got the labels right and the directions right. Maybe there's only 25% chance, but you get the point. The point is that because you're in a two-dimensional vector space, what you're doing when you're measuring spin up versus spin down or spin left versus spin right is you're making two different choices about how to talk about the vector that you have. Likewise, this vector psi, I can still write it in terms of components here. This is a different two sets of components in the different axes, spin left and spin right. All of which is to say, the difference between vertical spin and horizontal spin is not two separate quantities. It's two different ways of talking about the same underlying state that the thing could be in. And the reveal here, the reason why this is worth chatting about, is this is the origin of the uncertainty principle. Okay, remember we talked about the uncertainty principle in the context of position and momentum, and we said if you were completely localized in position, you had no idea what your momentum is, and we said if you're completely localized in momentum, you have no idea what your position is. The same thing is true for x spin and z spin. If you know what your x spin is, so let's say you know what your x spin is. Let's say you are purely spin right. Okay, let's draw you this way. Here is psi spin right. Okay, well then it's clear that you are maximally uncertain about whether you are spin up or spin down in the z direction, right? And likewise, if you were pure spin left, you would be maximally uncertain as well. And vice versa. If you were maximally certain about whether you were spin up or spin down in the z direction, you'd have no idea what your spin was in the x direction. So that's a reflection of the uncertainty principle. It's saying that if you believe the way that I suggested you think about it, there is no such thing as the x spin or z spin as an inherent property of the particle. These are outcomes of possible observations you can make, okay? They are not pre-existing things. And I'm emphasizing all this for a very good reason, because now let's start talking about entanglement, okay? Keep these equations in mind. The fact that up and down are related to left and right by this simple transformation, okay? So the questions come in because, the biggest question I really want to absolutely get around is an entanglement just kind of like classical correlations in some sense? So I want to talk about entanglement versus correlation. The example that was given, what if like you buy a packet of 2 gloves, okay? And you know that there's a left-handed glove and a right-handed glove in there. So you know that if you open one and pick one out at random, if it's the left-handed glove, you instantly know the other one is right-handed. Isn't entanglement just like that? So the answer is no. The entanglement is not just like that. Entanglement is more than that. And almost exactly that example was given by John Bell. He gave an example that he called Bertelsmann's socks. I'm not, again, completely clear that I'm spelling Bertelsmann's name right. So John Bell wrote, John Bell, when he was inventing the Bell inequalities, he's incredibly influenced by the Einstein-Podolsky-Rosen argument, the EPR argument, with these entangled spins. You can measure one and see what happens somewhere else. And so what he was trying to say is that entanglement is more than just classical correlation. So Bertelsmann's socks is the idea that this guy who was a friend of Bell's, another physicist at CERN, I think Reinhard Bertelsmann, he had this quirk of his personal style where when he wore socks, which was every day, but he would always wear 2 socks of different colors. Okay, they were never the same color. So Bell says if you see Bertelsmann coming down the hallway and he walks around a door and one of his legs is sticking out first, and you see, oh, on that leg he has a pink sock, then you instantly know that whatever is going on the other leg, it's not pink, because he always wears 2 different colored socks, okay? So that's an example of a classical correlation. You measure one thing and you know something just like it. You know something from it about something. From that, you know something about something completely different, okay? But Bell's point is that that's not what entanglement is for a few reasons. Let me just give you the most important reason here. We talked about, here's Alice and Bob with their spins. So here's Alice. She has a spin. Here's Bob, Planet Bob over here. There's another spin. And the state of both of them, by the way, these are called Bell states, this way of writing these spin states. There's a state that is 1 over square root of 2 spin up for Alice, spin down for Bob, just as an example. No, actually, it'll be easier for the subsequent math if I do both spins the same. Plus 1 over square root of 2, spin down for Alice, spin down for Bob. Remember, it doesn't matter whether or not they're aligned or anti-aligned. What matters is that they're related. What matters is if you measure one, then you instantly know the other one, okay? In either case, they would be entangled one way or the other. And so someone said, I think there was one question that said, isn't entanglement just the same as superposition, or at least what is the difference between them? So superposition is just possible with one particle, with one qubit, right? Here is a superposition. This is expressing the spin-up state as a superposition of spin right and spin left. And this is crucially important, by the way, again, we'll skip ahead a little bit. Note that people want to say sometimes, how many worlds are there in the many worlds theory of quantum mechanics? Or they want to say, when the electron goes through the double slits, is there a world in which it goes through the right-hand slit and a world in which it goes through the left-hand slit? And that is not my point of view at all. I know some people have points of view like that. David Deutsch has a point of view kind of like that. I don't want to try to say exactly what his point of view is, but it's related to that. It's sort of a fine-grained version of what the worlds are. My statement is that the worlds only come into existence when you experience decoherence. And we'll talk about that a little bit. Just writing it as a superposition doesn't mean it's two worlds at all. And that should be perfectly obvious, because this equation right here is saying that the same state can be written either as spin up 100% or an equal superposition of spin right and spin left. So is it one world or two worlds, right? It depends on how you write it, but that's silly. The number of worlds shouldn't depend on how you write it. And my way of figuring that out is just to say this is just one world because this spin is not entangled with anything at all. Entanglement is a relationship between two different parts of the quantum system. And when you only have one part, there's no such thing as entanglement, but there is superposition. Okay, so here is Alice and Bob, and if Alice measures her state and she finds it spin up, then Bob will measure his and he finds it spin up. But so I tried to get this across when I talked about the EPR experiment, but I think I didn't necessarily do a very good job, so let me try to do a little bit better. Sure, this is like Bertelsmann socks in the sense that if I measure the spin along the z direction, I know what Bob will get along the z direction. But I can use these equations, okay, for the state of one spin to rewrite this state of Alice and Bob in terms of spin left and spin right. In other words, Alice could choose to measure her spin along the z direction, and then we know what Bob will get along the z direction. But Alice could also choose independently, rather than measuring along the z direction, she could measure it along the x direction. And it turns out, if you go through the math, again, 50-50 chance I get the plus minus signs right here. But this is equivalent to spin right for Alice, spin right for Bob, plus 1 over square root of 2, spin left for Alice, spin left for Bob. Which means, again, modulo minus signs, which means that had Alice chosen to measure the spin along the x-axis instead of the z-axis, it would still be true that she knows what Bob is going to get. And the problem with that, the reason why that is profound and weird, is that, well, what Einstein and Podolsky and Rosen said is, look, I don't know what Alice is going to measure, and I don't know what answer she's going to get, but I can imagine that she measures something, and she's going to get something, okay? Let's say she gets spin up when she measures in the z direction. Then, if I refuse to countenance the possibility of spooky action at a distance, I instantly know what Bob's going to get. He's going to get spin up, okay? Therefore, EPR say, it must have always been the case that Bob was going to get spin up if he chose to measure the z-spin of his particle. Because Alice reveals that. There must be some pre-existing reality, is what EPR is saying, about about the z component of Bob's spin, namely that it was spin up, if we were in the world where when Alice measured, she was going to get spin up. And then they also say, look, Alice could have chosen to measure the x spin. She would have gotten some answer. Let's say it's spin right, okay? She gets n answers, all the point. It doesn't matter what the answer is. Let's say it's spin right. Then, instantly we know what Bob is going to get. But no signal can travel to Bob. Therefore, it must have always been the case that Bob was going to get spin right. So EPR say the whole point of their argument, which is often missed by people who talk about the argument, the whole point of their argument is it must be the case, if you don't have spooky action at a distance, that it was simultaneously true that Bob was always going to get spin up if he measured in the z direction, and he was always going to get spin right if he measured in the x direction. But quantum mechanics says that can never happen. That's the uncertainty principle. You cannot have a state of your particle in which with 100% certainty you will always get spin up if you measure along z, and spin right if you measure along x. Okay, so that's why they say quantum mechanics must be incomplete. And you see that this relationship is deeper than simple classical correlation, because the whole point of the socks is that there is some fact of the matter about what the socks are, right? You don't know what color Bertelsmann's socks are, but he knows. I mean, it's known. Someone could know. If you did know, you wouldn't be changing the condition of the world. You wouldn't be collapsing the wave function or anything like that. Quantum mechanical entanglement is a deeper and more profound phenomenon than that. There is no fact of the matter about whether Alice's spin is up or down before she measures it. There's also no fact of the matter about whether it's spin right or spin left before she measures it. And when she makes a measurement, we instantly know something new about what Bob is going to do. He doesn't know it, so we didn't send him a signal, but we instantly know something about it. Again, this is not something that has any analog in classical physics, okay? That's why Bell's theorem says that unless you do something like superdeterminism or many worlds, you need some non-locality in your theory of physics. And there's no non-locality needed to understand Bertelsmann's socks. So, there is a difference between quantum entanglement and classical correlation. That's important. Okay. Another question was, how do we entangle particles? And this is a very important question. Actually, I should have talked more about this, because this gets into the question of, is there a difference between entanglement, the process of entangling, versus simply interacting? Is it true that every time two quantum systems interact with each other, they become entangled or not, right? So no, it is not true that every time two quantum systems interact with each other, they become entangled. The point is that you entangle only when the two quantum systems interact in such a way that if you think about either one of those quantum systems as a superposition of different possibilities, then the two terms in the superposition interact differently with what you are interacting with, okay? So the classic example, I'm not going to draw the whole thing again, but Schrodinger's cat. We had the alive cat. There's the alive cat. And then we had the sleeping cat. Let sleeping cats lie here. And the point was that a photon in the environment could come along in such a way that if the cat were alive, the photon would hit the cat and be absorbed. Whereas if the cat were asleep, the photon would just go on its way. That is why the cat becomes entangled with the environment. If the cat is purely alive, it's still a quantum mechanical system, but every single, I say alive, and alive and asleep, awake, if the cat is purely awake, it's still a quantum mechanical system, but every photon that interacts with it in the same way. So no entanglement happens. The photon is either absorbed or not. It's only when the cat is in a superposition that the photon interacts differently with one term in the superposition versus another one. That's when entanglement happens. So if you like, think of an electron falling in a gravitational field, okay, rather than a magnetic field. The electron can be a superposition, spin up and spin down. It's clearly interacting with the gravitational field, right? Because it's falling, it's being pulled down. But both the spin up part and the spin down part fall exactly in the same way. Therefore, there is no entanglement between the gravitational field and the electron, okay? That's the difference between entanglement and interaction. Interaction can interact with the whole thing, all the terms in the superposition in the same way, no entanglement, or it can interact differentially with different terms in the superposition, and that's when you get entanglement. So how do you actually get it? How do you do it? Well, there's many different ways to do it. If you have two electrons, you can zap lasers at them using entangled photons and sort of transfer the entanglement to the electrons. Let me think of my favorite example, which is the decay of the Higgs boson. I think I didn't talk about this to you folks. I give this example all the time when I give talks on quantum mechanics. So the Higgs boson is a spin zero particle. So that means that it has no spin at all. It just sits there, right? Higgs. There it is. Not spinning at all. We discovered the Higgs boson in 2012. I wrote a book about it. I'm not going to show you the book, but there it is. It's a particle at the end of the universe. One of the things about the Higgs is it can decay. it can decay into, let's say, an electron and a positron, E plus and E minus, okay? And of course, they're going to go off in momentum back to back. Already that's entangled, right? This was the original example we gave of two entangled particles. We had them come in and scatter, so that they were not entangled when they came in, but they scattered and they were instantly entangled because different ways in which they scatter matter, right? If one scatters along one direction, the other scatters along the opposite direction. Boom, they're entangled. But this example is a little bit more clear. So the spin of this is spin 0. There's no spin at all. And let's say the Higgs boson is just sitting there, so it decays into an electron and a positron. They both have spin, but angular momentum is conserved, okay? So it must be the case that whatever the spins are of the electron and the positron, they have to be anti-aligned. They have to be going in different directions. So it could be, and there's a 1 over square root of 2 out here, it could be that the electron, that the positron is spin up and the electron is spin down. Or it could be that the positron is spin down and the electron is spin up. But it is some entangled superposition of both. So it is trivially easy to make entangled particles, just let a Higgs boson decay. There are easier ways to do it than that. Actually, pions are other particles that will decay into two spinning particles also. In fact, pions are probably a very easy way to do it because a pion is easier to make than a Higgs boson. They're much lighter, easier to produce, and they decay into photons moving back to back. And photons are polarized, either spinning clockwise or counterclockwise along the axis they're going on, not perpendicular to it, but the same exact kind of thing holds. The polarizations, the spins of the pions have to add to 0. The spins of the photons have to add to 0 since the original pion had 0 spin. So it's not at all difficult to make to make entangled particles. Finally, along this line, you might say, what about the double slit experiment? The double slit experiment, remember, I'm not going to do the thick lines again, sorry. But you had the source, and then it shot waves of electrons, and they either went through one or the other. And then you saw an interference pattern here, like that. So it's a very common question. Why doesn't the electron going through the slits count as a measurement all by itself? We said if you added a measurement device to look to see which slit the electron went through, then you would collapse the wave function, you break the interference pattern. But why doesn't the slits themselves, detector, why don't they count? Well, the answer is because the electron does not become entangled. And to be perfectly honest, in the usual way of talking about it, that's just assumed. The assumption is the slits or the barrier or whatever is a big heavy thing, and the electron just glances off of it without becoming entangled, okay? Now, you can do better than that. There's a wonderful little book by Yakir Aharonov, who's a famous physicist. Aharonov and oh no, I'm going to forget the other person's name. Well, he has a co-author. I'm very sorry, co-author. Rohrlich, I think it's Rohrlich. Aharonov and Rohrlich. A book, I think it's called Quantum Paradoxes. And they ask all these crazy questions about quantum mechanics, and they resolve the paradoxes. It's a way to teach you some of the more advanced features of the foundations of quantum theory. And one thing they do is say, well, what if we put our slits on wheels, right? Like, what if we put the double slit experiment, we put it on wheels so that when the electron goes through, it could actually nudge the momentum of the slits. Like, the slits are a quantum mechanical system. They have a wave function, they have a center of mass, a momentum, the whole bit. And then, well, you can actually go through the measurement and you can figure out, you can go through the calculation rather. I think it'd be very hard to do it in a real experiment, but you can go through the calculation, and guess what? It depends on how heavy the barrier is. If it's a big, heavy thing, the electron's not going to become that entangled with it, and it's going to be exactly the double slit experiment as we described it here. If it's a light, very easily disturbed barrier, then the electron will become entangled with it, because the momentum of the electron going one way will push the barrier in one direction, going the other way will push it in the other one. So all this is just to say, there's a little bit of entanglement that might happen, but you can ignore it if you just do the experiment correctly. And if you don't want to ignore it, you can do the calculation correctly. You can put all those factors back in, get the right answer, you're in good shape. Okay. One tiny question, which I'm not quite sure how to answer. Let me say, I'm quite sure how to answer a question. I'm not sure exactly if it was the question that it was being asked. And the question is, what space is the wave function in? And what is meant by this, of course, I said wave functions are elements of Hilbert space, this vector space, this set of all quantum states. But if you think about this experiment we just did, one electron going through the double slits being detected by the detector, it looks like the wave function psi is just a function of space and maybe of time also, right? So that just looks like a function of space. Why is it looks like the wave function is in space. There it is at every point. There's a value for the wave function. Why do you say it's in this big infinite dimensional vector space? So two answers to that. One is, of course, it depends on what you mean by the word in. In is not necessarily a technical term in physics or mathematics. Element of is a technical term. So this idea, if you only have one electron and you ignore its spin, so all it has is a position, then indeed the wave function psi can be thought of as a map, as we talked about before. The wave function at one moment of time is a map from space, R3, to the complex numbers, okay? For every location in space, there is a complex number, the wave function of the electron. But this does not mean that psi is in R3, it's that in space. It means that it's a function on space. That's a different thing. This psi is an element of Hilbert space, which is the space of all possible wave functions, which is infinite dimensional, because there's an infinite number of distinct, perpendicular to each other wave functions that you can imagine writing down. So that's the most trivial answer to this question. There's a difference between being a function on a space and being an element of a space. But there's a more sophisticated construal of what's meant by here. When you have two electrons, two particles, let's say, I'll say particles because I want to ignore spins now after having made a big deal of them previously. When you have two particles, the wave function, as we know, is a function of the positions of both of them. Okay, that's the origin of the possibility of entanglement. So for that wave function, it's a map from two copies of space to the complex numbers, right? And two copies of space is just three-dimensional Euclidean space, R3, that's equal to R6. And indeed, for n particles, psi works out to be a map from R3n to the complex numbers. And this is called configuration space for n particles. So what this is saying is, you have some collection of n particles, you tell me the set of all possible configurations they can be in, that is the space that a wave function is on. That is the space that the wave function maps from that space to the complex numbers. And this is why wave functions are not classical fields. Classical fields, electric field, magnetic field, gravitational field, all of these fields are independently functions of space. You tell me where you are in space, and I can tell you the gravitational field, the magnetic field, the electric field, etc. The wave function is not. Once you're beyond one particle, you can't just say, here I am at a point in space, what is the wave function? That's not how it works. You have to tell me the configuration of all the possible particles. And of course, as we discussed, trust me, as we will discuss very, very soon, when you go to field theory, it becomes much more complicated, okay? Then you have a field all over space, and you're talking about the configuration space of the field, the space of all possible field configurations, is already a big infinite dimensional space. And the wave function maps that space into the complex numbers, okay? So it's mathematically a little bit more abstract, nonsensical, but it makes perfect sense. You can actually do all the math in it. So even at this level of saying what space is the wave function a function of, it's not space, okay? It's the configuration space for whatever thing you're looking at. And we also said, by the way, that you could equally well think of the wave function of a particle as the wave function of momentum. So you can't do both. It's not a function of position and momentum. It's a function of position or momentum, and you can do that for n particles also. And that only makes sense because just like the set of positions is three-dimensional, the set of momenta is three-dimensional. In fact, in any space of d dimensions, if you have a d-dimensional configuration space, you're going to have a d-dimensional momentum space also. So that's why it can possibly work out that the wave function lives equally well in either space. Okay. People, I did want to say this because people argue a lot about whether configuration space, whether this whole thing means that configuration space is real. Like, do we really live in configuration space, this big space? If you have 20 particles, this is 60-dimensional space already. And if you have 10 to the 88th particles, you know, you have about 10 to the 88th dimensions, roughly speaking, 3 times 10 to the 88th dimensions. You really have an infinite number of dimensions once you have a field, and maybe you have less than that with quantum gravity. But anyway, I would say you live in Hilbert space. That is what our universe has a wave function and that lives in. It is an element of Hilbert space. It's a different thing than being a function on a space. Okay, good. Good. So I think that that's what I wanted to say about entanglement and the nature of entanglement. And then we can get into the fun topic of probability in the many worlds interpretation. Again, this is something that I have talked about before in lectures, but we should mention it here. Probability, I'm not going to have the general notion about probability, but probability in many worlds interpretation. I said that interpretation is not the right word to use for these theories, but it's what people use, so there you go. This is the single biggest challenge. Well, this is one of the two biggest challenges to many worlds. I think one challenge is the way in which the empirical world around us, which has three-dimensional space, time, you know, planets and tables and chairs and people interacting in an almost classical way, the emergence of the classical world, or many copies of the classical world, from this big abstract wave function. I think that's one big problem. And the other big problem is the origin of probability. I think both these problems are very solvable. That's why I'm pro many worlds, but they're absolutely out there. These are the respectable problems. These are the issues where if you say, I don't believe in the many worlds interpretation because of this problem, I will go, well, okay, you have a right to do that, okay? If you say, I don't believe in the many worlds interpretation because it's too many worlds, then I'm just going to go, all right, whatever. But probability is a really big problem because in the textbook formulation of quantum mechanics, when you say I have a state of a qubit that is alpha spin up plus beta spin down, and I say I have a probability of observing spin up, which is just given by alpha squared, and likewise for beta squared. Can't write and talk at the same time. What that means is something will happen in the conventional textbook interpretation. Something will happen. I don't know what will happen. I'll get spin up or spin down. But I know that if I do it over and over again, if I'm a good frequentist about my probability, I can define the probability of something as what the fraction of outcomes would be were I to do the experiment an infinite number of times. Okay, that's a frequentist notion of probability. It makes perfect sense with respect to the conventional Copenhagen interpretation of quantum mechanics. You can imagine measuring a system in this state over and over and over again. Every time you measure it, the wave function collapses, but you can re-prepare it in this state. So you can manipulate your electron with magnetic fields or lasers or whatever, measure it again, do that many, many times. Okay. That's not what happens in many worlds. In many worlds, there's no collapse. So what I should do is be very explicit here. In the conventional Copenhagen interpretation, you measure it, and then it becomes, this is psi 1, and psi 2 is just up. And that's it, with the probability of alpha squared. Or it becomes down, with probability down is beta squared. So it becomes one or the other. Whereas in many worlds, so this is textbook. In many worlds, psi 1 equals alpha up. And then you have some apparatus and an environment. You have to do the whole thing, right? So this is the spin. Then you have an apparatus, which is in 0 state for the apparatus and 0 state for the environment. Let me actually move this out over here. You have the spin in a superposition as before, but you need to keep track of everything else. There you go. And then time evolution just means the Schrodinger equation. There's no mystical collapses or anything like that. And you get to psi 2, we're skipping some steps, but it becomes alpha, spin is up, apparatus measured the spin to be up, environment is whatever it was, having seen the apparatus measure it to be spin up, plus beta, Spin is down. Apparatus saw it down. Environment is whatever the environment would be in the world where the apparatus measured the spin to be down. And that's it. You're done. This is supposed to be the whole Manyworlds interpretation. There's no words in there about probability of observing anything. But empirically, our experimental history is that when we measure things, we get different probabilities, with alpha squared and beta squared being the different probabilities we get. So here, in this wave function, the only thing to say that has the word probability in it is, with probability 1, both spin up and spin down will be observed by somebody, okay? Will be observed by somebody on one branch or the other. And so many different attitudes have been proposed towards doing this. People have said, well, can't you just use as a postulate that you find yourself in the spin up branch or the spin down branch with probability alpha squared or beta squared? That doesn't work. There's no such thing as finding yourself in that sense. There is a copy of you that is in the spin up branch, and there is a copy of you that is in the spin down branch. And you know that will be true with probability 1, okay? To the people in these branches, these numbers, alpha and beta, they're just going along for the ride. What do they have to do with anything? They didn't touch anything. If I live here, if I think that I'm the apparatus, okay? So if this is me, let me call this the spin-up version of me, and this is the spin-down version of me. Well, I don't know anything about alpha and beta. They're just outside, multiplying my world in the wave function of the universe. But who cares? Why should that affect my epistemic state, my state about what I know about the universe? Okay. So the origin of probability at all in the Manyworlds interpretation is a common conundrum. And what you might say, so one thing is, can you just add as a postulate? The answer is no, you can't, because the postulates are done. The whole idea of Manyworlds was there are wave functions, they're in Hilbert space, they obey the Schrodinger equation. That's it. Everything else you're supposed to derive. Okay, no room for extra postulates. The other thing you could do is maybe each branch has equal probability, right? There are two, think about if you lived in a big universe. And the universe was so big, much, much bigger than the universe we actually observe outside. The universe was so big that with very high probability, there's an exact copy of you living somewhere else. So it's a very big universe, and someplace bajillions of light years away, here's you, and here's an exact copy of you, or is this one you, and this is the copy? Which one is you and which one is the copy? They're identical. Which one is you? Well, you don't know. Maybe you know everything there is to know about the universe, but you don't know which of these two people you are. This is called self-locating uncertainty. You know everything there is to know about the universe, except where you are in it. Also sometimes called indexical uncertainty. So one way of dealing with self-locating uncertainty is to say, well, look, these are two copies of me in the big universe case. They're completely indistinguishable. They're identical locally. There's not like any wristband that says I'm the one on the left, okay? So I should give 50-50. I should give equal credence, as we say. The credence is your degree of personal belief that you are one or the other. You're completely ignorant. There's two identical situations. Give them equal credence, therefore equal probability. In a Bayesian way of thinking about probability, as opposed to a frequentist way, a Bayesian way of thinking about probability says probabilities are just expressions of our ignorance. There is some fact of the matter, or there might be, but we don't know. Okay, so when we talk about the probability that the Philadelphia 76ers are going to win the NBA championship whenever the NBA championship is next held, okay, that's not a frequentist probability. They're not going to have the NBA championship an infinite number of times, at least not the 2020 NBA championship. I'm using this example intentionally because in my book, Something Deeply Hidden, I said, we know that there will be a 2020 NBA championship, but we don't know who will win it. I did not anticipate that we don't even know whether there will be a 2020 NBA championship. This makes me very sad. Sorry about that. The point is, though, we use probability talk to discuss things where we don't know what the answer is, even though there is only one answer, and there's not multiple different copies. There's not multiple different ways of doing the experiment over and over again. So we talk about assigning credences in these cases. Bayesian notions of probability are exactly fitted to that situation, where what probability is just a measure of your ignorance, and as you gain more information, you can update what your credence is, and then therefore you can change the credences and the probabilities you assign to things. Okay, so this doesn't work. This equal probability, this, let's give equal credence to all the alternatives, doesn't work in quantum mechanics. It certainly doesn't work in this example I gave unless alpha and beta are equal to each other, or at least equal to each other in magnitude, right? Because that is not the Born rule. The Born rule says the probability is alpha squared or beta squared, not 50-50. If alpha was the square root of 0.99 and beta is the square root of 0.01, you don't want to give these equal probabilities. Also, it shouldn't work, right? We shouldn't be surprised that it doesn't work, and let me explain to you why. So imagine that you have, let's say, what's the right way to do this? Yeah, let's say that you have two spins, okay? And they're both in two spins, and they're both, once again, I should really plan out these videos more than I do, but they're both in, let's call it spin 1 and spin 2. So spin 1 is in equal superposition of up and down, and so is spin 2. And I'll explain why in a second. 1 over square root of 2, spin up, plus 1 over square root of 2, spin down. I think this is going to work. I'm going to have to change the numbers in a second, but okay. The point is you arrange the following situation. You measure the spin along the z direction of spin 1. Okay, so here you are with two spins, psi 1, psi 2. And then you're going to measure spin 1. And you're either going to get spin up or spin down for spin 1, okay? Now there are two copies of you, two branches of the wave function, right? And you're tempted to say, well, I give them equal probability, right? That maybe you're tempted to do that. Let's imagine you're tempted to do that. But then you make an arrangement with yourself that if you get spin down, you will measure again. You will measure spin 2. If you don't get spin down, you don't measure spin 2. So spin 1 is just up here, and spin 2 is just remaining the same. But now you measure spin 2, and you can get spin up or spin down for spin 2. And now there are 3 branches to the wave function. So if you're really consistent, here you want to assign probabilities, 1/2, 1/2, because there are 2 branches, and you said, I'm going to assign equal weight to all the branches. But here, there are 3 branches, so you should assign weight 1/3, 1/3, 1/3. But what in the world happened here? Like, if I'm on the spin up branch, and I start by assigning it probability spin 1/2, and then something happens on another branch of the wave function, and suddenly I should assign a different probability to my branch? That makes no sense. I'm in a different world. My world does not change its probability just because someone else is doing something in another world, okay? So this idea that you weight the branches equally doesn't work. It's just not a starter. There was no reason to do it in the first place, and it also doesn't actually pay off. Okay, so let's do a slightly better example, an example that does work. So the thing that you can do that does work is instead of saying I assign equal branches to all, equal probability to each branch, say to yourself, I assign equal probability to branches that have the same amplitude. Okay, I assign equal probability if and only if the wave function assigns an amplitude to that branch which is equal to the other branch. Okay, so now we're seeing that the amplitudes could matter, and that's going to be important. So let me change my experiment a little bit here. No, actually, I can keep that. I can keep spin 2 as it is. Oops. White, good. So spin 2 is still an equal superposition of spin up and spin down. But imagine that spin 1 is an unequal superposition. so that I say this is square root of 1/3 spin up, square root of 2/3 spin down. Let's just say, I'm picking my experiment here, okay? And now, I start with psi 1, psi 2. I measure spin 1. I get either it's up or it's down. And I do the same thing. If it's up, it's just up. If it's down, I'm going to measure spin 2. And I can find that that's either up or down. And when I'm here, either here or here, before I've measured spin 2, the amplitude here is square root of 1/3. And the amplitude here is square root of 2/3. So those are not equal. And therefore I say my rule, which says I have equal probability if I have equal amplitudes, doesn't help me. Doesn't tell me what the probability is, okay? Just doesn't give me any information at all, so I can't say anything yet. But when I measure spin 2, then this square root of 2/3 gets multiplied by that square root of 1/2. And now this is 1/3, and this is 1/3. And therefore, and this is, well, it's the square root of 1/3. The amplitude is the square root of 1/3. And this is still the square root of 1/3. And so now these three branches have the same amplitude, square root of 1/3. So now I can assign them equal probability. And there are three of them, and I assign them equal probability. So the equal probability is 1/3, 1/3, 1/3. And if I do that, then I know what the probability was before I measured spin 2, because I want to make it consistent. So if the top branch has probability 1/3, then it always did. So I should put a 1/3 here. And if the two branches where I measured spin 2, if they both have probability 1/3, then the combination of them better have probability 2/3, right? But you notice that now the probabilities I've assigned are exactly the amplitude squared. That's the Born rule, okay? So in Manyworlds, if you make the argument that branches with equal amplitudes should be given equal credences that you're on them, you should resolve your self-locating uncertainty by saying not that I give every branch equal likelihood, but I give branches equal likelihood when they have the same wave function, when they have the same amplitude. Then you derive that the Born rule is the one consistent way of assigning probabilities in Manyworlds. Now you might argue, well, even when the wave function, even when the amplitudes are equal, why should I give equal credence? And that's a longer story, actually. That's the hard part. I mean, if I had started with saying that, you probably would have said, sure, I'll let you do that. Now you're more a little skeptical, but there are very good reasons to do that also. So this is a version of an argument that's been given in different forms by Wojtek Zurek, Chip Siebens, my colleague at Caltech, and I wrote a version of this argument that explicitly uses self-locating uncertainty, which Zurek didn't do. And there's another way of proving Manyworlds gets the Born rule from decision theory, from David Deutsch and David Wallace. So in my mind, we mostly understand. There's some fiddly things here that I think you can still pick at in terms of the logical structure of the argument, but I'm 98% happy that the Born rule is the right way to think about probability in Manyworlds. You can disagree, that's okay. There are principled ways of disagreeing because, as I said before, Manyworlds is different. The metaphysics of all these worlds and all these copies of you is something that we didn't grow up thinking about, okay? Something that we haven't developed the mental technology to really deal with. And this is what we're trying to do in experiments like this, in papers like this, like Chip Siebens and I wrote, etc. We're trying to expand our human logic and way of thinking to a world where the wave function branches, and there are many copies of us. We will undoubtedly make mistakes along the way, and maybe it's all a waste of time because it's not the right interpretation of quantum mechanics, but it is science. We are doing science, we are making progress, we can do better than just say, well, this makes me uncomfortable or I don't like it. We actually have to sort of address these problems head on and figure them out. And whatever it is, as I said in Something Deeply Hidden many times, I am not invested in Manyworlds being the correct interpretation of quantum mechanics. I happen to think it is, but if it turns out to be something else, I'm fine. What I'm invested in is people caring about the correct interpretation of quantum mechanics, whatever it is. We need to figure it out. There's many reasons we should think it figure it out. Not only in principle, it's our job to figure things out, but because it will be helpful understanding physics moving forward. There's a lot of questions in physics we don't know the answer to. Understanding quantum mechanics would help us quite a bit.